We're constantly hearing about the incredible things AI can do, right? Writing poetry, generating code, it's amazing. But today, we're going to pop the hood and actually look at the engine that makes it all possible. And more importantly, how that engine is being completely reinvented as we speak. You know, AI can feel like total magic. You type in a question, and this complex, coherent answer just appears. But here's the thing, it's not magic. It's just really, really clever engineering. So, how does an AI actually think? To get that, we need to rewind the clock a bit. So, our story really starts with this fundamental problem. How in the world do you teach a machine, a thing of pure logic, of ones and zeros, to understand something as messy and beautiful as human language? Well, the first most obvious idea was, hey, let's just teach computers to read the way we do, sequentially, one word at a time, left to right, and hopefully build up some meaning along the way. Seemed logical, but this approach came with some pretty serious baggage. This led to the first big architecture for the job called a recurrent neural network, or RNN for short. The best way to think about it is like someone reading a super long book. It reads the first word, jots down a little note, reads the second word, updates the note, and so on. The hope was that it could build up context by remembering everything that came before. But you can probably guess where this is going. There was a massive problem. Just like you might forget the details from chapter 1 by the time you hit chapter 30, the RNN's memory of the beginning of a long paragraph would just fade away. Technologically, this is called the vanishing gradient problem, and it meant the model had no idea how to connect a word at the end of a sentence to the thing it was talking about way back at the start. Oh, and on top of that, reading one word at a time was just painfully slow. So, okay, this one word at a time thing, it was a dead end, a huge bottleneck. The whole field needed a completely different idea, something radical. What if a machine didn't have to read like a human? What if it could just look at the entire sentence, or even the whole document, all at once? And boy, did that radical idea arrive. In 2017, a new concept dropped that sparked a revolution. It led directly to the AI we're all using today. This was the birth of the transformer. It all kicked off with this one, now legendary, paper from a team at Google. And the title says it all. It was a real statement. Attention is all you need. They were basically saying, let's throw out that old, slow, word-by-word system and replace it with something totally new. And that something was a mechanism called self-attention. So forget reading left to right. Self-attention is like giving the model superpowers. It can look at every single word in a sentence at the exact same time and instantly figure out how important each word is to every other word. It just sees all the connections at once, no matter how far apart they are. And that, right there, was the game changer. The exact thing RNNs were terrible at, connecting distant words, transformers could do effortlessly. This ability to see everything in parallel was a massive leap forward, and it's what gave us models like GPT. But like all great superpowers, this one had a secret weakness. A really, really big one. Yeah, that amazing ability to process everything at once? It wasn't free. Not even close. In fact, it created a totally new kind of problem, one that researchers are still battling with today. It turns out the very thing that made the transformers so powerful was also its Achilles heel. Because as you feed it more and more text, the amount of work it has to do doesn't just go up, it explodes. The technical term for this is quadratic complexity. Okay, here's the best way to get this. Think of a party. If you have 10 guests, there's a certain number of possible one-on-one conversations. But if you double the guests to 20, you don't just double the conversations, you quadruple them. Every new person has to be able to talk to you every other person. Self-attention works exactly the same way. Let's put some numbers on this, because this is where it gets crazy. Let's say processing 100 words takes 10,000 units of work. If you just double the input to 200 words, the workload doesn't double to 20,000. Nope, it skyrockets to 40,000. It's this exponential growth that makes it basically impossible to feed an entire book into a standard transformer. So this crazy scaling problem basically fired the starting pistol on a brand new race in AI research. The mission? Figure out how to keep the awesome power of the transformer, but replace its inefficient attention engine with something way faster, something that could actually scale. And researchers started trying all sorts of clever hacks to get around this. Some ideas, like sparse attention, try to force the model to only pay attention to a few important words. Others, like linear attention, try to use simpler math to get a good enough answer. And then you have totally new ideas, like a new family of models called extractors, which just rethink the whole problem from the ground up.
Okay, so take a look at this. This is a peek inside a standard transformer. Don't worry about all the boxes, just focus on this one in the middle, the multi-head attention block. This thing is the engine. It's the powerhouse, but it's also the gas guzzler, causing our scaling problem.
And this is where things get really, really cool. The new idea isn't to junk the whole transformer design. It's to do an engine swap. What if we could just pull out that one inefficient part and drop in something better? The big idea is to literally design a new part, like these extractors, that you can just drop right into that same spot. It's designed to take the same inputs, give the same kind of outputs, but on the inside, it works in a completely different and way more efficient way. So what exactly is this extractor thing? Well, it's a new type of drop-in replacement. Instead of making every word look at every other word, which is super expensive, it just tries to pull out a single, unified summary of the most important features from the whole sentence. It gets the context it needs without the crazy computational cost. And you don't have to take my word for it. The proof is right here in the data. This chart shows a head-to-head comparison. On the left, you have standard self-attention. On the right, a new extractor model. The bar represents the training cost, basically how hard it is for the model to learn. And as you can see, lower is better. The new extractor isn't just more efficient, it actually learns better. So what does all this geeky engineering stuff actually mean? Well, it means we are right on the edge of another huge leap forward. We went from slow, sequential models to powerful parallel transformers, and now we're moving toward a new generation of incredibly efficient AI. And this isn't just some academic thought experiment. It has huge real-world consequences. I mean, why should you care? Because a more efficient AI is an AI that can take on massively bigger jobs. I mean, just think about it. An AI that can read an entire library of medical research, not just a paper, the whole library. Or analyze a company's entire decade of financial reports, or sift through 1 million lines of code in seconds. It means these powerful tools get cheaper, more accessible, and open the door to things like perfect, real-time translation that we've only ever dreamed of. Look, the attention mechanism, that was the revolution that gave us the AI of today. But now we're finding ways to replace it with something even better, something faster and smarter. And that just leaves us with one thrilling question. If attention gave us all this, what on earth is its successor going to unlock for us tomorrow?